Welcome one and all to the second lesson on the chapter of statistical distributions for the stats portion of the Year 12 course. So the last chapter we looked at, chapter 6.1, was just going through the basics from some of the statistical distributions you might encounter and how to illustrate those, in particular in tables. There's also something called a probability mass function too. And so 6.1 laid the foundation, but the main thing in this chapter is something called the binomial distribution, which is essentially an easier way of imagining a infinite or near infinite tree diagram. All will become clear if you think that sounds a bit strange, but before we start properly, of course, let's have a look at the warm-up questions now. So here they are. 4 to kick you off. Question 1 is a Venn diagram one. Question 2 relates directly to today, as does 3 to an extent, and question 4 will relate to the last bit of the chapter, next lesson, chapter 6.3. So have a go at these independently, press pause now, and when you're ready to see the solutions, press play, and I'll guide you through these warm-ups. Okay, well, let's have a look now at question number 1. So we've got here 2 events, A and B, and some information about them. So we've got the probability that the event lies in the intersection of A and not B is 0.08. The probability that the event lies in the intersection of B and not A, the complement of A, is 0.48, and the probability of it being A or B or both is 0.68. So first of all, we need to draw a Venn diagram to show this information. So we need something like this to begin with, and from here we can populate the information as needed. So first of all, let's consider whereabouts the region A intersection B dashed would be. So this here means all of A which overlaps with what is not B. Okay, so normally that would be all of A, but we only want it with the stuff that isn't including B, and so we don't want anything to do with B, and so what we want is all of A apart from that which is anything to do with B. And so it's just this region of the diagram here, just this portion of the circle or ellipse that represents A. So in this, we can fill in 0.08. Sometimes I wonder why I bother colouring in. I don't know, maybe it harks back to childhood where I liked colouring in. Who knows? Anyway, that's 0.08. Next, we're told the probability of the event being in the intersection of not A and B combined. That's 0.48. And so this, likewise, is just the centre of the circle B without the left-hand side of it. So it's the only portion of the circle B which doesn't have anything to do with a bit of overlaps with circle A. So it's the centre bit of this circle and the right-hand side bit. And so we're told what this probability is of the event lying here. It's 0.48. And so we just fill in with this one, 0.48. We're then told that the probability of it being A or B or both is 0.68. So A or B or both is anywhere within these 2 circles, including the overlapping bit. So the total of all these 3 sections needs to be 0.68. So to work out this middle bit, we can get our Classwiz and just simply do 0.68 minus these 2. So 0.68 minus 0.08 minus 0.48, that gives us 0.12, which goes in the middle. A common mistake here is for students to think, well, I'm done now, but actually you've got to remember the possibility that the event has nothing to do with A or B. So there's going to be a number almost always on the outside. As you should know, the sum of all probabilities for any one event should add up to 1. Right here they don't, these just total 0.68. So to work out the number just on the edge of the rectangle, we need to do 1 subtract 0.68. And if we do that, 1 minus 0.68 gives us 0.32. We've now done part A of question 1, so we can now think about part B. Part B asks us to show that A and B are independent. Now, if they're independent, what we're going to have here is the probability of A multiplied by the probability of B will equal the probability of the event being the intersection of A and B. Okay, so let's work these out separately, and they should equal each other. So the probability of A is essentially the chance that the event lies within this circle here for A. And so within the circle of A, we've got 0.08 and also 0.12. So add these two together, we get 0.2. And then for B, the chance of the event lying inside B is this region of B, 0.48, plus this overlapping region of B, 2, because this is also part of B. So 0.12 plus 0.48 is 0.6. So therefore, the probability of A multiplied by the probability of B is 0.2 multiplied by 0.6, which gives us 0.12. And we can see here that the probability of the event being in the intersection of A and B, which is this overlapping section, is just 0.12 from before. And so we've just shown that the probability of A times the probability of B is equal to the probability of the intersection, which proves that the events are independent. So we'll just conclude by going back to the original statement. So therefore, we can say A and B are independent. I'll remind you of some fancy mathematical notation now as well, just for the sake of it, because it's an upside down triangle. Because PA times PB equals the probability of A and the intersection of B. So that's question 1 sorted. Let's now have a look at question 2. So question 2 talks about pool. So when Sean plays Jamie in a game of pool, the probability of Sean winning is 0.4. So normally Sean doesn't stand much of a chance against Jamie, sadly. Well, sadly for Sean anyway. Now, if they play 4 games and the outcome of each game is independent, we need to find the probability that Sean loses the first 3 games but wins the 4th game. So here what we're talking about, because the outcome needs to be independent, that means that if Sean loses one game and then another, he's not going to get disheartened. He's going to maintain the same probability of winning. In the same way, we have to assume that Jamie's not going to get too overconfident and increase his probability of winning. So we're making the assumption here that this probability of Sean winning of being 0.4 is fixed and constant throughout. So this can only happen if Sean loses the first 3 games and then wins the last. So it's a probability of lose, 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 win. For Sean anyway. So the probability of losing is going to be 0.6 for Sean. Remember, if the chance of him winning is 0.4, 1 minus 0.4 gives a chance of him not winning. Pool is a binary game. You can't draw a game of pool. It's a win or a loss. So 1 minus 0.4 is 0.6. And then, so multiply, losing the second game is 0.6. And then losing the third game, multiply by another 0.6. And finally, the chance of him winning the last is 0.4. So just get our calculators up and ready and bang this into it and see what we get. So 0.6, we can do that to the power 3 to save ourselves some time, and then multiply by 0.4, and indeed we get 0.0864. So roughly a 9% chance of that happening. Seems a low probability, but that's because there's many other combinations of things that could happen in a 4-game series. Let's now have a look at question 3. Find the x to the power 4 term in this binomial expansion. So now I'm just going to remind you of how to expand a binomial. So 2 minus x to the 7. First of all, we start with 7, choose 0. The power of the first term, the 2, starts at 7, the same value as this, and the power of the second term in the bracket is 0. We then, with consecutive terms, follow a certain pattern, and the pattern is this value here increases by 1 each time, so the next one will be 7, choose 1. This power here of 2 decreases by 1 each time, whereas the power of the final thing is going to increase by 1 each time. And so we're going to keep on going, and what's more, when we get confident with the pattern, we can just skip ahead to the term we're wanting, which is the x to the power 4 term. And so this is going to be, as you can see here, where the power of a minus x is going to be to the power 4. These two powers will always add up to the number of this one here. So 6 plus 1 is 7, 7 plus 0 is 7. So if we need minus x to the power 4, that means our 2 is going to be to the power 3. Another thing to spot with these patterns is that this bottom number is always the same as the power of the second term in the bracket. So because we want this to be power 4, our bottom number is a 4, and the top number, as ever, because it's power 7, is 7. And so the x to the power 4 term is going to be this one. And we can essentially ignore all the other terms because the question isn't asking us about any other term apart from this one. So therefore, the x to the power 4 term is going to be this calculation. So on the calculator, we need to type in 7, choose 4. So we do 7, shift, divide 4, multiply by 2 to the power 3. Now, when we do minus x to the power 4, if we multiply something by an even power, it will always come out to be positive. And so the numerical work we just leave here, then we're going to attach an x to the power 4 at the end. So we get 280. So the coefficient of x to the power 4 is 280. In other words, we're going to have 280 x to the power 4 for our x to the power 4 term. Finally, let's have a look at warm-up question 4. So complete the table. Now this will make more sense when you have a look at the next lesson. So it's just a rephrasing of how we can put the words into a calculation. With a binomial expansion, which we're going to see in a moment, how we interpret the question is absolutely key to getting the calculations correct. So what we need to end up with in this final column is something where we have probability of x being equal or less than some value. That's what we're wanting here. So in this case, question mark was 5. So if we want something to be no more than 3, that means that we want the unknown x to be less than 4. Alternatively, as a calculation, we can work out the probability that x is equal to 3 or less than 3. So no more than 3 means this. Next up, at least 7. That means we want x to be at least 7. So we want x to be greater than 6, assuming x is going to be a whole number, this is. So if we're interested in it being at least 7, that means we're not interested in 6 or under. So we do 1 minus the probability that x is 6 or under. This calculation here will leave us with everything where x is 7 or higher, because we're getting rid of, we're subtracting, the option that it's 6 or less. So at least 7 means this. Next up, fewer than 4. That means we want x to be less than 4. So if you see here, no more than 3 and fewer than 4, it's essentially the same thing when we're talking about whole numbers. No more than 3 means we can have 3, 2, 1. Fewer than 4 again means 3, 2, 1 or 0. So again, this means exactly the same thing. And finally, at most 8, that means it can equal 8. So we want x to be up to and including 8, but no more. So that's what we're wanting. Or alternatively, what we could have is we could say here that we want x to be less than 9. So as an alternate way of thinking about it, if you want to, we could have here that x is less than 9. Using this symbol here, it means we want to calculate the probability that x is up to and including 8, but no more. So that's the warm-up done. Let's now have a look at the main bit of this session. So here, I want to just introduce to you the binomial distribution. And so what is it? How does it work? Why is it useful? So let's just go back to question 2 of the warm-up. The probability of Sean winning any one game of pool is 0.4. Therefore, from this, we also know that the probability of Jamie winning any one game is 0.6. So if Sean doesn't win, then that means Jamie wins. 0.4 plus 0.6 adds up to 1. Now, if we assume again that each game is independent, we can represent all probabilities of the 4 game outcomes on a tree diagram as shown on the next screen. So that's the first branch for the first game. Either Sean wins S or Jamie wins J in red. So just one branch for the first game. Now let's introduce a second branch for the second game. So again, the 0.4 and 0.6 outcomes are fixed, so more complexity is added. Another branch would be for the third game. Now this is why I've drawn it for you in the notes. Doing a tree diagram of this complexity would A, take ages to draw out, and B, because it's so complex, it would enable lots of potential for mistakes to be made, which isn't good. And finally, if you can imagine drawing an extra branch for the fourth game, you'd have something like this. So at the end, you'd have 16 different outcomes for the 16 different routes down all the branches. And you might want to notice as well that 16 is 2 to the power 4. And as well on your notes, you've got this, where these are the spaces to fill in the probabilities of going down each and every branch. So this is an activity for you. At this point, I want you to read the student activity questions and spend as much time as you need, maybe up to 15-20 minutes, tackling these questions on the student activity. So press pause now and press play only when you want to compare your results to mine and just check that you've got them right. Okay, so assuming you're doing that and you're pressing play to see, I'm going to talk you through the solutions to this activity. So I'm just putting this tree diagram to the side for a moment. So the activity, question 1, was for the tree diagram, use your calculator to complete the 16 probabilities to the right of the diagram. So let's start at the top. What's the probability that Sean wins all 4 games? We're looking at the very top branch here. 0.4 times 0.4 times 0.4 times 0.4. 0.4 to the power 4. If you did that, you should have got 0.0256. The next one, Sean wins the first 3 and Jamie wins the last one. This is going down this branch. Sean, 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 Jamie. So 0.4 times 0.4 times 0.4 times 0.6. That should have given you 0.0384. The next branch is 0.4, 0.4, then Jamie wins, which is 0.6, then multiply by 0.4. You should have got this value. Now, if we just carry on just a bit quicker, you should see some patterns forming. So that's for Sean winning the first 2 and Jamie winning the last 2. The chance of Sean winning the first, Jamie the second, then Sean the last 2 is 0.0384. The probability of it going Sean, Jamie, then Sean, Jamie is 0.0576. The probability of Sean, then Jamie, Jamie, then Sean is 0.0576 again. Probability of Sean winning the first and losing the next 3 is 0.0864. Probability of Jamie winning the first and Sean winning the last 3 is 0.0384. JSSJ 0.0576. JSJS 0.0576. JSJJ 0.0864. JJSS is 0.0576. JJSJ is 0.0864. JJJS is 0.0864, and finally the chance of Jamie winning all 4 games, probability of JJJJ, is 0.1296. And now I'm going to pause to catch my breath. Whew. Right, hopefully now, if you weren't sure already, you can hopefully see that doing a tree diagram for something this complex would not be a good idea, which begs the question perhaps, why am I doing it at all? I'm going to show you the link between a tree diagram and the binomial distribution, which the calculator can do for you in a split second. So if you can understand the link, it will deepen your understanding. That's my idea anyway. So let's have a look now at the next question. So it says, using these completed probabilities for all 4 of the games, calculate the probability that Sean loses all of the 4 games. So how many ways can that happen? So I'm going to highlight this in a colour. So if we highlight in yellow the route or routes where Sean loses all 4 of the games, it's just going to be the route where Jamie wins all 4. So there's only one way that Sean can lose all 4 games. That's if Jamie beats him every single time, which is this yellow route highlighted here, which therefore is 0.1296, about a 13% chance. Part B. The chance that Sean wins exactly 1 game, how many routes are there for this? Well, here we're after this one here. This one is where he wins just once. This route here, and also this one. So I'm going to highlight this in a different colour, which is green, and you should see there's 4 different paths. And each path has this same probability associated with it. So the total probability of Sean winning exactly 1 game is 0.0864 multiplied by 1, 2, 3, 4, which gives us 0.3456. Part C. How many routes would there be where Sean wins exactly 2 games, in other words, where they win 2 games each? So I'm going to highlight this in a blue colour. Ask yourself, how many routes can you see? How many paths, starting from the beginning, going all the way to the end? Is it 3? Is it 4? Actually, there's 6 paths, which I've highlighted here in this light blue colour. Each one has a probability of 0.0576. Because there's 6 such paths, the total probability of Sean winning exactly 2 games is 6 multiplied by 0.0576, which gives us, again weirdly, 0.3456. Part D. What's the chance that Sean wins exactly 3 games? Again, if I pick a colour to highlight this, let's go for purple, you should find there's 4 ways this can happen, each with a probability of 0.0384. Therefore, the total probability of Sean winning exactly 3 is 0.0384 multiplied by these different 4, which gives us 0.1536. And finally, last but not least, the chance of Sean winning all of the 4 games, just one way of that happening, which is just this very top branch here. So if I highlight this in a pretty pink colour, you can see that that's a 0.0256 chance of happening. You could check that these values are right by adding up all of these, and you should get a grand total of 1. Because if Sean plays 4 games, he has to win either 0, 1, 2, 3 or 4. This covers all probabilities, so this adds up to 1, which it does. You check for yourself if you want to. So, next up, Part 3a. We're asked to write out the complete binomial expansion of 0.6j plus 0.4s to the power 4. And so this is going to be, we start with 4, choose 0, 0.6j to the power 4, and 0.4s is going to be to the power 0. Now this 0 is going to increase by 1 each time, so the next one is going to be 4, choose 1, 0.6j, that goes down to a 3, 0.4s goes up to 1. Then we have 4, choose 2, 0.6j, we're going to square that one, then 0.4s, we're going to square, not much space here. Then 4 choose 3, 0.6j cubed. Sorry, 0.6j, that goes down to a 1, my apologies. I'm trying to rush and I've made a mistake on the pattern, which is not good. That should be power 1, apologies. Then 0.4s is now to the power 3. And finally, we're going to have 4 choose 4. Then 0.6j to the power 0. 0.4s to the power 4. Now, if we work this out, we should find something quite interesting indeed. Just before I carry out the calculation on this, though, I'm just going to shift it to one side because in my old traditional way, I've not left myself much space on the right-hand side to actually perform the calculation. So if I just shunt this slightly to the left, like so, then I'll have a bit more space to actually write this out. So what we need to do first is the coefficient of j to the power 4. So if we do this now, we're going to get 4 choose 0 multiplied by 0.6 to the power 4. And if you really want to, you can do multiplied by 0.6 to the power 0, but that'll give you 1 anyway. So there'll be no s's and nothing to do with 0.4. So it'll just be the coefficient of j to the power 4. And we have here 0.1296. And so the first one is 0.1296 j to the power 4. Next, we have a look at this one here. So next time, it's 4 choose 1, 0.6 cubed times 0.4. And this will give us the coefficient of j cubed s. So what we can do here is just adapt what we've already got on the calculator, which sometimes saves time. So now we want 4 choose 1. I made a pig 0 of that, never mind. 4 shift divide 1. Then multiplied by 0.6 cubed, then we multiply by 0.4 to the power 1. And that gives us 0.3456 j cubed s. So we write that down next. So 0.3456 j cubed s. I apologise for the tiny writing. This is what I always do, and my students are well aware that I never seem to leave myself enough space, which is very annoying for myself as well. Anyway, carrying on, the chance of winning exactly 2 games is going to be this coefficient here. 4 choose 2, 0.6 squared, 0.4 squared. That's going to be the coefficient of j squared, s squared. And so here, we can alter what we've already got. So we type in 4 choose 2 next time. So delete then a 2, 0.6 squared, 0.4 squared. Press equals, and again we get 0.3456. So plus 0.3456. At this point, I'm going to give up trying to squeeze it all on. I think I'm fighting a losing battle. So j squared, s squared. So I'll just go here next time. Then winning exactly 3 games, we're looking at this coefficient, the penultimate one. So 4 choose 3, 0.6 to the power 1, 0.4 to the power 3. So I'll just move the calculator out of the way so we can see it. So 4 choose 3, 0.6 just to the power 1 this time. And 0.4 cubed. And I get 0.1536. And so the next one is 0.1536 j s cubed. And the final one is just 4 choose 4, 0.6j to the 0, and 0.4s to the power 4. And so 4 choose 4, 4 choose 0 and 4 choose 4 is always 1, but I'm just including it so you can see the pattern clearly. 0.6 to the power 0, that's just going to be 1. Anything to the power 0 is 1, remember. And 0.4 to the power 4, that's going to give us 0.0256. So we have 0.0256. That's just going to be s to the power 4. And so that's the entirety of the expansion done. What we now need to do is compare these coefficients to what we had from part 2. So now let's have a look at free part B. So free part B, we have to compare the coefficients of j to the power 4, j cubed s, j squared s squared, js cubed, and s to the power 4 in that expansion we've just done to the answers from 2a, b, c, d and d. What do we notice? So if we just have a look here, we should notice, as I've mentioned before, something quite peculiar. So the coefficient of j to the power 4 is 0.1296, which is what we had here. The coefficient of j cubed s is 0.3456. Again, we had exactly that. The coefficient of j squared s squared is 0.3456, which is exactly what we had from part C. From part D, the coefficient of js cubed is 0.1536. And again, as you can probably guess, it's exactly the same thing. And finally, again, what the same thing is the coefficient of s to the power 4, which is 0.0256, which is precisely what we had here. So in terms of what we notice, they are the same. And so by using a calculator, by using what we know about this binomial expansion from the chapter in the pure side of the course, we can actually fast track ever having to do a very long, complicated tree diagram where the probabilities are fixed. We don't ever have to do that again unless a question were to ask. And so this here is pretty amazing indeed. Next up, it's saying here in the tree diagram, compare how many paths there are. For example, just picking this at random am here, where Sean wins 2 of the 4 games to the binomial coefficient of 4 choose 2. Again, what do we notice? Well, 4 choose 2 is basically there's 4 games, he's won 2. That's how it relates to 2 of the 4. We're picking 2 from the 4. So this is what highlighted in the light blue. And you can see here, there's a path here at the bottom, 1, 2, slightly higher, there's a third path, then a fourth one, and a fifth one, and finally a sixth one very near the top. So there's 6 different paths. And if you were to try for binomial expansion 4 choose 2, you get 6. So again, it's exactly the same. So what do we notice? It's the same. And so the binomial expansion has all of this built into it, which is a beautiful pattern indeed. So again, they are the same. I'm going to put again an exclamation mark because I think that is cool to say the least. So what we can do here is try and generalize these results and get a formula which we can apply to a wide variety of questions in the future to help us, and to do such questions much quicker than having to do a tree diagram. So now, at this stage, let's see if we can piece all this together into something more useful in general. So we can now see, like I've said, how such probability distributions are inextricably linked to the general binomial expansion we studied earlier in the academic year in the pure algebra side of the course. So as such, these distributions are called binomial distributions. So what does a random variable have to be in order to be modelled appropriately as a binomial distribution? Well, there needs to be a few things. First of all, what you need is a fixed number of trials. So in our case, it was 4 specific pool games. It wasn't 5 or 6, it was clearly 4. The trials are independent of each other. So what that's saying is a probability of one game is independent of a probability of the other game. The probabilities are fixed. There are only two possible outcomes, so none of this is win or lose, success or failure, get a job, don't get a job, whatever it might be. It needs to be binary, either one or the other. Binary, in other words, has to be binomial. And finally, the probabilities of the two outcomes have to remain the same throughout the trials. So the probabilities have to be independent of one another, and also they must be fixed. So in our case, when we were having the games of pool, we could define the random variable x as a number of games that Sean wins, where the probability of Sean winning each game is 0.4. Then what we could do is work out all of these probabilities of him winning 0 games, 1 game, 2, 3, or all 4 games. And just a reminder of what we had from before, this is the distribution from before, and in bold are the coefficients. So the probability of him winning no games was the coefficient of j to the power 4. In other words, it's the same as when Jamie won all games, which is 0.1296. The probability of winning just one game is this one here, where the power of s is just 1, so that's 0.3456. Winning 2 games, s squared for 2 games, again 0.3456. Don't read anything into these being the same too much. It's not necessarily the case for different questions. It might be, it might not. The probability of him winning 3 games is this coefficient here of s cubed, which is 0.1536. And finally, the chance of him winning all 4 games is the coefficient of s to the 4, which is 0.0256. And indeed, if you added all these numbers up, you would get a grand total of precisely 1. So just again, to have this on the screen to talk about, can we see any patterns in this? Well, we can hopefully now see that the probability mass function, which we discussed in 6.1, for this particular binomial distribution, where there's 4 trials, probability of success is 0.4, can be written as this. The probability that the distribution, the number of games won, equals r, is 4 choose r, 0.4 to the power r, 0.6 to the power of 4 take r, where r has to be an integer value, in this case a positive whole number, and r ranges from 0, where no games are won by Sean, all the way up to 4 games, where he wins all 4 of the 4. So can we go further with this? How does 0.4 and 0.6, how do they relate to each other? Well, hopefully you can see that these sum to 1. So whatever this number is here, this value will be 1 minus this one. So we can generalize this even further. So, and again, if more games were added, each iteration of a tree diagram would make it more complex to the point where drawing it wouldn't be practical. So the previous tree diagram, I'm sure you can agree, was complicated enough. So if we generalize the above result, like I said, if this 0.4, we can call that p, this value here is just 1 minus that value. So if I call it generally p, the probability of a success or a win or whatever, this value here will be 1 minus p. And so this here is the particular probability mass function of a general binomial distribution. In this case, n is the number of trials, p is a probability of success, and r varies from 0 all the way up to where r is the same as n. And again, like I mentioned before, for a random variable to be appropriately modelled as a binomial distribution, we must have these 4 things. A fixed number of trials, which is called n. The trials are independent of one another. There are only 2 possible outcomes, either win or lose, success or failure typically. And finally, the probability of success, which is p, has to remain the same throughout all trials. So let's add a bit more to this. How do we write it down? Well, if a random variable is modelled by a binomial distribution, we write x, this symbol here, which is a tilde, capital B for binomial, and then n and p are the particular things which it's modelled on. So index is n. N is essentially how many things we're having, the number of trials, and p is the number, and p is a probability of success. So it's easier with examples, obviously. What makes it even easier than just doing examples with a tree diagram is how can we get the Classwiz to do the hard work for us. So using the Classwiz to calculate particular binomial probabilities of a type of a probability that the distribution takes on a particular value. At this stage, it'd be handy if you had your Classwiz calculators to hand. So what we can do is get it up and ready, something like this. So you might not have seen this display yet, so I'm going to talk you through key press by key press how you get to this. Okay, so what we're going to do is we're going to press from the main menu these buttons. And in case you think I'm making it up, I'm going to show you on mine. Okay, so I'm going to go back to the main menu by just pressing the on button. So press on. So we press menu first of all. So menu, then down, right, right. So down, right, right. You'll see here it's option 7. We press equals. Then option 4. This stands for binomial probability distribution. So option 4. And then press 2 for variable. If you're wondering what list is, maybe ask me in the comments section or in class. I'm not going to open that can of worms today. We're just going to focus on variable. So then press option 2. And you should have something like this. In other words, the calculator should look something like this. And so x is the value you want to find the probability of. N is the number of trials. P is a probability of success. So if I just return very quickly to those games of pool from before, let's imagine we wanted to work out the probability of Sean winning 2 of the 4 games. There's 4 games in total, so we'd press N as being 4. The number of games you want to calculate the probability of him winning is 2. So we scroll up and say 2. Press 2, then equals. Then for P, we type in the probability of success, which in our case is a probability of Sean winning. So we type in here 0.4. And that's press equals again. That's what we get. And if you compare that to the notes from before, that is indeed the probability of Sean winning 2 out of the 4 games. Well, let's now have a look at a couple of questions which aren't pool related. So apologies if you were sick of me talking about the pool. It doesn't really matter what I was talking about. It's more so about the pattern and the binomial expansion which lies underneath the surface. Anyway, moving on from all that, we have here a random variable x which is binomially distributed such that x follows binomial. It's got 10 trials. Probability of success is 0.3. For part A, we need to work out the probability that the variable is 2. So what's the probability of 2 successes given this information? And so I'm going to show you now using a Classwiz. And so what we're going to do is just get the calculator up and ready like so. So we go into this mode. I'm going to show you how to get to it again. So it's menu, go to distribution, which is 7, press equals, press 4 for binomial PD, then variable. So what we have here is our n number of trials is 10, so we need to change this number here to a 10. Press equals. We want to work out the probability that it's a 2, so we change the little x to a 2. And the probability of success, we're told, if I just move along, is 0.3. So if I type in 0.3, so 10, I want to work out the chance of having 2 successes if the probability of each success is 0.3. Press equals and sit back and let the calculator do all the legwork for you. It's awesome. So what we have here to 3 significant figures is 0.233. And that's it to 3 significant figures. So let's have a look at part B now. So part B, we want the chance that x is anywhere up to and including 2. So what could it be if it's up to and including 2? Well, we could have where there's no successes at all, or plus we could have it where the number of successes is exactly 1, or finally we could have it where the number of successes is exactly 2. Now at this point, if you're wondering, is there a way the calculator can just work out cumulative ones, 0, 1 and 2 together for you? Yes, there is, and that big reveal is the next lesson. That'll be on the video for 6.3. So all will be revealed. For now though, I just want to use the binomial PD function. So let's do this. So if I press AC to get back, so what I want here is the chance of x being 2, which we had from before. Okay, so just to remind ourselves, that's 0.23347. I'm going to give it to some extra accuracy to avoid any rounding error. So 0.23347. So just to colour code, so you're wondering, in case you're wondering where the numbers are coming from, this is a chance of it being equal to 2. Next, I'm going to add the probability of it being equal to 1. So press AC, toggle this x to be 1 now, press equals and equals again. That's 0.12106. 12106. And finally, the probability that it's equal to 0. So if I now press AC and press X equal to 0, I get 0.028248. 0.028248. So I'm just going to double check that I've typed it in correctly, as I think I have, but it can't hurt to just make sure. 0.028248, yes. So I'm almost trying to get you hungry for thinking there must be a quicker way. There is, but I'm going to reveal it all next time. So for now, we'll just add up these 3 values, the yellow, the green, and the light blue. So if we do that, go back to normal mode on your calculator. So menu 1, 0.23347 plus 0.12106, then plus 0.028248, press equals, and round it to 3 significant figures. We get 0.383. And that's correct to 3 significant figures. Finally, C, probability that x is greater than 8. So how can we work this one out? For probability that x is greater than 8, if there's 10 trials, then that means that either x is equal to 9, or it's a probability that x is equal to 10. So we need to work out when x is equal to 9, the chance of that, and add it to the chance of x being equal to 10. So again, we get the calculator ready to go. I'll move it along so you can see what's going on. Press menu, scroll to 7, press equals, binomial PD, so press 4, go for variable, which is 2, and now I'm going to type in that we want 9, my mistake. So we want 9 successes from a total of n, which is 10. The probability of each success is 0.3. Press equals and equals again. This is minuscule. So 0.000, I'm going to give that 138. I'm going to round that to 3 significant figures. So 0.000138. Now, why is this number so tiny? Well, if you think about it, just take a step back and think what we're saying. we're saying that this event, the probability of it happening is 0.3. So it's only 30% likely to happen. So if you've got 10 trials and this thing is only 30% likely to happen for any one trial, you'd expect maybe 2 or 3 times out of 10 it would happen. So to happen 9 times out of 10 when it's so unlikely, that'd be particularly freakish. That'd be really, really rare, hence this low probability. And this one here is going to be even smaller. 0.3 times 0.3 all the way to the power 10. So on the calculator, what we do, we press AC, change the x to a 10, and see this number shrink even smaller. Look at this, absolutely minuscule. So we've got 0 and 0, 0, 0, 0, 0. So 1, 2, 3, 4, 5 zeros after the decimal point. One, 2, 3, 4, 5, like I've said. 1, 2, 3, 4, 5. And then we've got 5, 9, 0. So now if we go back to normal mode and add these together, so menu 1 for normal, 0.000, sometimes double press, which is annoying, 138 plus 0.00000, 1, 2, 3, 4, 5, 590. We get this. So now we can round this to 3 significant figures. So we get 0.00014. 0.0000144. And we can round that, because that was given to 3 significant figures. So it's about 0.01% chance of happening. Very, very unlikely to happen indeed. Finally, D. How could we have it so that this variable is between 1 and 4 non-inclusive? The only way this could happen is if the variable takes on a value of 2, or if the variable takes on a value of being exactly equal to 3. So again, we can now calculate this using the calculator. So menu, switch to mode 7, binomial PD, variable, so type 2, 10 trials, so type 10, probability of success is 0.3, equals and equals again. We get 0.23347, which is what we had from before from part A and part B, so 0.23347. Then switch it to a 3, so press AC, change x from a 2 to a 3, press equals, and equals again to calculate. We get 0.26683, so 0.26683. So now if we add these two values together, so go back to menu 1 to get into the normal mode, so 0.23347 plus 0.26683. So press equals, see what we get. We get 0.500. So to 3 sig figs, almost exactly half, 50% chance. So it's just a case of getting used to using the calculator functions on the calculator and very little more. Up to this stage anyway, it will get a bit more complex. Let's have a look at the final worked example now. So worked example 2. A company manufactures light bulbs in an automated factory. So the probability that a defective light bulb is chosen at random from the production line is 0.07, so that's tiny. Let x be the number of defective light bulbs chosen at random. State any assumptions that are required to model the number of defective light bulbs in a sample size n as a binomial distribution. This is essentially a memory test, something you need to remember and regurgitate for the exam. I have seen this asked before. So what you'd need is any 3 from the following. So you need a fixed number of light bulbs, which is n. The probability of a light bulb being defective has to be independent of the other light bulbs being defective or not. Each light bulb can be classed as either defective or not defective, so it's a case of being one or the other, hence it's binomial. And finally, the probability of a light bulb being defective has to be the same for all light bulbs. So now we can do part B, once we've got that boring stuff out of the way, if I can dare say so as a maths teacher. So part B, using the model, find the probability that exactly 2 light bulbs are defective. So first of all, let's just write down what it is. This is binomial. Okay, we're talking about 50 light bulbs here, so our n is 50. The probability of a light bulb being defective is 0.07. So this is going to be our way into tackling this question for part B. In terms of where these numbers have come from, 50 is the number of light bulbs, that's a sample size, and 0.07 is the probability of it being defective, which is from the top line here. So now, probability for exactly 2 are defective just means the probability for x equals 2 from this distribution. So again, the calculator, I'll show you from scratch how to get it. So what we need to do is we press menu, go down to mode 7, press equals, binomial PD, press 4, variable, so option 2. Now we type in these values. So we want to work out the chance of 2 being defective, so our little x is 2. Total number n of light bulbs being tested is 50, so type in 50. The probability of a defect, p, is 0.07. So press equals to code it all in, then equals again to generate our solution, and we get to 3 different figures, 0.184. So there's roughly an 18% chance of out of 50 light bulbs, 3 might throw a fault. Which is not unreasonable really. If the chance of a fault is only about 7%, then expect a few to be faulty. 18% is unlikely, but about a 1 in 6 chance you'd get 3. That's to be expected, more or less. If you got here that, for example, the chance of 40 of them being faulty was this number, you'd raise an eyebrow because you should expect not very many at all to be faulty, with only a 7% chance per light bulb having a fault on it. So that's all from me. What I want you to do now is to practice some of these yourselves. So if you can turn to page 91 in the Stats and Mechanics book for year 12, it's exercise 6b, and attempt all of the exam type questions and problem solving questions, all the ones which say an E and a P next to them. Those are the questions that closely follow what you might encounter in a real exam. So try those, master those, check your answers regularly. If you're getting stuck, ask somebody you're working next to, check the answers and work backwards. If you're still stuck, that's where I come in. Either let me know in class, email me, or even leave a comment on the video comment section below. Thank you very much for listening. Do consider subscribing, that would be very nice of you, and I hope to see and hear from you very soon. Thanks for now, take care, goodbye.